Hello, hello, hello. Okay, so we're going to actually have 3 videos. The first video covers the first 2 pages on energy, solids, and liquids. So these are the answers. I hope you can actually read them. So we have an equation, first of all. Q equals mc delta T. Q is the energy, m is the mass of the substance, C is the heat capacity. We'll talk about that in a second. Delta T is the change in temperature. So Q and delta T are proportional to each other. If the temperature is increasing, then the Q value should be positive because the energy is increasing. If the temperature is decreasing, then delta T will be negative. And since the temperature is decreasing, we should have a negative value for Q. What the heck is heat capacity then? C, the capacity of a substance to take in energy or give off energy as a function of temperature. You can think of this as how energy moves in and out of your substance. If it takes in energy very easily, this value tends to be small. If it resists taking in energy, this value tends to be very large. We're measuring energy, so we need some units, and these are our units, joules and calories. These are used interchangeably quite often. We do need to be able to convert between the two, and so the conversion is right here. 1 calorie is 4.184. That's an 8 joules. You've got to be able to convert between both of those. A calorie is the amount of energy needed to change a gram of water by 1 degree Celsius. So if you put like say you imagine you're burning a match or something, and all that heat is coming out of the match, it's going into 1 gram of water. If the temperature goes up 1 degree Celsius, then the match has released 1 calorie of energy. That would also mean, since that's 1 calorie, that it's 4.184 joules. Water is probably the most common substance we talk about. More on that in a second. So let's look at this question. Again, we're using Q equals mc delta T. We'll read the problem. We have 15.75 grams. That's the mass. Here is the heat. This is Q. This is the energy. Oops, that's uppercase. That'll be okay. Its temperature changes from 25 to 175. That is an increase of 150 degrees Celsius. That is our delta T. It increases by 150 degrees Celsius. Calculate the heat capacity. So we plug the numbers in. Q, M, don't know C, delta T. So we need to do the math. Multiply 15 times 150, and then we divide those into 1086, and we get the heat capacity. This is a small heat capacity, which makes sense since it's a metal. That's less than 1. Less than 1 thing, you can throw that out. It's just a small heat capacity. It's very low. How many joules of heat are needed to raise the temperature of 10 grams? Here's the mass. From 22 to 55. 55 minus 22 means the temperature is changing by 33 degrees Celsius. And then we have the heat capacity as 0.9, so that's our C. Multiply these together. These grams cancel those grams. Celsius cancels Celsius. The only unit left is joules. Yay! Alright. Pause if you need more time to write. Next page. Alright, number 7 is kind of the same idea. We have water. Now, the one thing you won't be given with water is its heat capacity. You should know the heat capacity of water. It is always either given in, it's either used in calories or joules. If it's calories, then the heat capacity for water in calories would be 1 calorie per gram per degree Celsius. 1. We would just usually write 1 calorie per gram degree Celsius. If it was in joules, then it would be 4.184 joules per gram degree Celsius. So in number 7, we have 100 milliliters, which, because the density of water is 1, gram per milliliter, that means we have 100 grams of water. That is our mass. We have 100 grams of water, and its temperature goes from 4 to 37. 4 to 37, that's an increase of 33 degrees Celsius. Calculate the amount of energy needed to cause it to rise this much. It doesn't say what units to use. So in this, we've got Q, M. For the heat capacity, we're using the calories one right here, 1 calorie per gram degree Celsius, and the temperature change. And we got 3,300 calories. If instead you used joules, just multiply this answer by 4.184, and you've got the answer in joules, 13,800 joules. Some of the weird things about that again, the heat capacity for water is one of the few you need to know, because it is also the same as the conversion between calories and joules. 1 calorie per gram degree Celsius, 1 joule per gram degree Celsius. I mean 4.184, whoa, whoa, whoa. 4.184 joules per gram degree Celsius is the heat capacity in joules. My fault. What is the specific heat? Some more Mr. Shangraw's silver metal. It's 55 grams of metal, 47 calories have been put into it. Temperature rises by 15 degrees Celsius. They are telling us the delta T right there. They're saying that it changed by 15. Plug in the Q, plug in the mass, plug in the delta T. We can solve for the heat capacity. Wow, heat capacity for silver is really low. Interesting. All right, number 9. What temperature must 50 grams of glass? What temperature will 50 grams of glass rise to? Oh, here's our mass. If it absorbs 5,275 joules of heat, that's our Q. Its capacity is 0.5. So right there, we have the mass, the Q, the heat capacity. We could solve for delta T. So let's solve for delta T. Mass, delta T is 211. So its temperature is going to increase by 211 degrees. That's 211 degrees Celsius for the delta T, the change in temperature. It's going up by that much. Well, it says it started at 20 degrees Celsius. So it starts at 20, goes up by 211. That's where we're getting this 231 degrees Celsius, because that's what it's going to end at. All right. Switching gears. Here's the first law of thermodynamics, called the law of conservation of energy. It says that either energy is neither created nor destroyed. It only changes form. So energy flows out of one substance into another substance. The temperature changes. Reactions occur. They give off heat. The surroundings take in the heat. Molecules move around faster. Molecules move around slower. It just keeps changing form, but it doesn't ever decrease. Numero 11, page 2. There, we flipped the page. In a calorimeter, the assumption is that the energy gained by one part of the system is the same as the energy lost by the other. In class, you did a lab. You had a styrofoam cup. This is obviously a styrofoam cup. Look at it. It's beautiful. And it had water in it. Oh, definitely water. And then you took a hot piece of metal, and you put this hot piece of metal into this water, and the energy came out of the metal and into the water. And we assumed that it worked perfectly, that the energy out of the metal was equal to the energy into the water. However, the signs are opposite. So if the Q of the metal was negative, the Q of the water was positive. Heat out of the metal into the water. Equal but opposite. Number 12. A 2.7 gram piece of metal is heated to 98.7. It's then added to a water beaker that contains 150 milliliters of water. At this, the final temperature of the water in the metal is this. What is the heat capacity of the metal? This is a lot like our lab. So first, let's analyze the water. We have the mass of the water. We have the heat capacity for water, 4.184 joules per gram degree Celsius, and the temperature change for the water. The water goes from 23.5 to 25.2. There's that temperature change. This is the delta T. So we multiply these three things together. Now we know what the water is taking in, right? We know what the water is taking in. Where does the energy come from that's going into the water? It's coming out of the metal. So here we have the mass of the metal and the temperature change of the metal, and what's missing there is the heat capacity of the metal, pins blocking it. If we solve for the heat capacity, we know the heat capacity of the metal. This is a pretty high heat capacity for a metal. 5 is greater than the heat capacity for water. That's kind of weird. That's a big, big heat capacity. Number 13. An exothermic reaction, the chemical potential energy of the products is less than or greater than that of the reactants. So it's exothermic, so energy is flowing out, so the amount of potential energy should be decreasing. So the products should have less than the reactants. So here we have a graph of potential energy versus the reaction. This side would be the reactants, this side is the products, and as the reaction proceeds, bam, you lose energy, and the products end up having less. Probably the most common example of this is always combustion reactions. You have your hydrocarbon, you have your paper, whatever, gasoline. You light it on fire and make ashes. The ashes have less potential energy to release than the previous thing. Have you ever tried to burn just ashes? It's quite difficult. There's not much energy stored up in those bonds, whereas the original thing was very easy to burn. But anyway, potential energy decreasing when it's exothermic. 14 is the reverse of that question. It is an endothermic question. We've got a little diagram here where the reactants versus the products. See, there's an increase overall. Here, let's just scale this. Let's say this was 3 joules, 6 joules. So its energy is increasing up to 6 and then dropping down maybe back to 5. But overall, we're going from 3 to 5, which means we have a total increase of 2 joules or kilojoules or whatever. So the product should have more energy or greater potential energy. Classify the following as exo or endothermic. Is released, exothermic. Metabolism of glucose in the body, meaning we're breaking apart sugar, exothermic. You're using the energy when you break it apart. Is absorbed, going in, endothermic. Water turning into vapor. This is from the perspective of the water. You are putting energy into the water to boil it or vaporize it. Formation of sleet. You have to take energy. Formation of sleet from water. You have to take energy from the water to make sleet. You take the energy out of the water, and the energy leaves the water, it then can freeze and turn into sleet. Photosynthesis, definitely endothermic. It's taking in light and converting carbon dioxide and water into different types of starches and glucose and sucrose. That is very endothermic, using the sun's power to change the compounds. Cooking a pancake, super endothermic. I mean, you've got it on a, I was going to say flipping pan. That's oddly appropriate. You've got it sitting on a flipping pan, and the pancake is taking in heat. You then flip it over, it lands on the other side, and it puts in energy on that side. That's definitely endothermic and oddly funny. Decomposition reaction, we're decomposing things. Decomposition reaction, here's a pretty standard one. Calcium carbonate breaks apart into calcium oxide and carbon dioxide. Almost always we are putting energy into this thing. We're heating a reactant and breaking it apart, so it's endothermic. Dry ice going from solid to gas. Anytime you go from solid to gas, the solid is absorbing energy to break intermolecular bonds. In this case, very weak ones. We'll talk more about intermolecular bonds later in another video. Burning gasoline, it's hot. It's exothermic. Gives off heat. Chemical ice pack. If it's an ice pack, it should be taking in heat. When we mix some chemicals together, like water and ammonium nitrate, they take in heat. You just mix them up, gets cold. It's pretty cool because of the reaction. needs to take in heat. When I say it gets cold, meaning the reactants are reacting and absorbing energy, so it feels cold because it's taking energy out of the surroundings. Alright, those are the first 2 pages. I'm going to stop and start again in part 2.